So to start off with, let us cover our cost diagram, which is extremely important. Your cost diagram is responsible for reduction, simplifying, co-functions, co-ratios, most of the stuff, your diagram questions as well. So most of the stuff that you do in trig relies on your cost diagram. General solution also relies on your cost diagram. So to do general solution, you also need your cost diagram. So essentially, if you know your cost diagram, you basically know most of the stuff in trig. So let's start. Whenever we are dealing with our cost diagram, something important to take note of is that we have two different ways angles can be represented. Angles can be represented as positive angles or negative angles. Now, how do we determine if something is a positive angle or if it is a negative angle? It's based on the direction that it goes in. So if our angle is moving in a anti-clockwise direction, so think of clockwise as the direction in which the hands on your watch move. If you use an analog watch, your hands usually move in a clockwise direction. So an anti-clockwise direction would be opposite to that. So when we are dealing with positive angles, they move in an anti-clockwise direction. Now, our quadrants, we have 4 quadrants that are broken up into 90 degrees each. So within quadrant 1, we have 0 degrees to 90 degrees. So anything that is smaller than 90 degrees but bigger than 0 degrees is considered to be within quadrant 1. So 2 degrees, 10 degrees, 45 degrees, 70 degrees, 89 degrees. Those are some examples. So anything within 0 to 90 degrees is considered to be within quadrant 1. And our reduction formula within quadrant 1 is theta as well as 90 minus theta. So those are the 2 reduction formulas that you should be familiar with within quadrant 1. Now, what is positive within quadrant 1? We know that everything within quadrant 1 is going to be positive. That is why we denote quadrant 1 with an A to show that all is positive, which means that sine of theta will be positive, cos of theta will be positive, and tan of theta will be positive within quadrant 1. Now we have another reduction formula that we can associate with quadrant 1 as well. Although it's not something that is frequently used or quite popular, we can also remember it in case it does pop up, which is 360 plus theta. So anything that is more than 360, or if you have 360 plus an angle, we'll associate it with quadrant 1. Keeping in mind that it cannot go beyond 450. So a side note is, whenever you're dealing with something bigger than 360, always subtract 360 until you get to something that is less than 360. That'll make it easier for you to apply your reduction formula. Now, this is quadrant 1. If we move on into quadrant 2, which is from 90 degrees until 180 degrees. That is 91 degrees, 92 degrees, 100 degrees, 150, 160, even 179. All of that falls within, all of those are examples of the angles that fall within quadrant 2. Now within quadrant 2, we have the reduction formula 90 plus theta, as well as 180 minus theta. So those are 2 of the reduction formula that you should be familiar with when you're dealing with quadrant 2. Now, formulas involving 90 are co-ratios or co-functions, whichever you prefer to call them. We'll have a look at those a bit later. Now, what is positive and what is negative within quadrant 2? So within quadrant 2, we have S, because remember our cost diagram is CAST. So we have S within quadrant 2, which means that only sine is positive. So we can say sine theta is positive, but cos theta and tan theta will be negative. So it's important to know these things. You'll see later on when we look at some questions, you'll see how this cost diagram can be applied to your reduction formula, reduction questions, your simplifying expression questions. And in Tuesday's session, you'll see how we can apply to general solution. Now, if we look at quadrant 3, that is anything within 180 degrees to 270 degrees. Now, our reduction formula for that quadrant is 180 plus theta. So we're saying anything greater than 180 up to and including 270 degrees. So from 180 degrees to, or instead, a better way to put it would be between, not up to including, sorry about that. It would be between 180 degrees to 270 degrees. So from 181 or even 180.5, so anything bigger than 180 degrees but less than 270 degrees would be considered quadrant 3. Now, what is positive within quadrant 3? So we have T within quadrant 3. That means that only tan is positive, which means anything that is not tan is going to be negative. So sine is going to be negative, cos is going to be negative, but tan will be positive. So far we've done quadrants 1, 2, and 3. Let us move on to quadrant 4, which is our last and final quadrant, before we move on to negative angles. So within quadrant 4, that is anything that is greater than 270 degrees, but less than 360 degrees. Now, our reduction formula for quadrant 4 is 360 degrees minus theta. And what is positive and what is negative within quadrant 4? So because we have a C within quadrant 4, we know that cos will be positive, whereas everything else will be negative. So sine theta will be negative, cos theta will be positive, and tan theta will be negative. So our cost diagram, C represents cos, A represents all, S represents sine, and T represents tan. So hopefully everyone should be okay with that. Let us move on to our negative angles, our negative quadrants. So if we move on to negative angles, the first question that should pop up is, if positive angles were moving in an anti-clockwise direction, what direction would negative angles be moving in? Now, negative angles move in a clockwise direction, the same direction that the hands on your analog watch move in. So within a clockwise direction. Now, our quadrants are still the same, quadrant 1, quadrant 2, quadrant 3, and quadrant 4 within our negative angles. So how do we get our positive cost diagram, or rather, how do we get our negative cost diagram from our positive cost diagram? It's easy. All we do is we multiply everything by a negative, right? So all you need to do is remember, or if you want to memorize your first cost diagram, diagram, your positive angle cost diagram. If you are able to memorize or remember your positive angle cost diagram, you can then get your negative angle cost diagram without even remembering it. All you have to do is multiply everything within your positive cost diagram by a negative. So let's look at quadrant 4. Before we do that, let's just put our CAST. And that is still the same, CAST cost. It's still in the exact same quadrants. So let's start with quadrant 4, since we are moving in the negative direction. So if we look at quadrant 4, we know that costs is the only thing that is going to be positive, which means that sine and tan are going to be negative. So cos theta will be positive, whereas sine theta is going to be negative, and tan theta is also going to be negative. Now let us identify what is our reduction formula going to be within quadrant 4. So if you notice, the arrow is different, right? Previously, we had a positive cost diagram. The arrow moved in an anti-clockwise direction, meaning that we started off with quadrant 1. But if we look at our negative cost diagram, our negative angle diagram, we can see that the arrow is moving in a downwards direction, meaning that we are starting with quadrant 4. So essentially, we're starting with the opposite sides. Previously, we started with quadrant 1 and went to quadrant 4. Now we're starting with quadrant 4 and going to quadrant 1. So we look at our starting point previously. We started with quadrant 1. So now that starting point, quadrant 1, is going to be multiplied by a negative, and that's going to be our new starting point as quadrant 4. So we have 90 minus theta and theta. That is our starting point. So let's write this here. We have theta and 90 minus theta. Now, previously I mentioned that if you want to get your negative angles or your negative cost diagram, all you do is multiply by a negative. So if we have positive theta, if we multiply positive theta by negative, that is going to give us negative theta. So that is our reduction formula for quadrant 4. Excuse me. Now let's look at our second reduction formula, 90 minus theta. If we were to multiply this by a negative, we would end up with negative 90 plus theta, because positive 90 times a negative gives us negative 90, and negative theta times a negative gives us positive theta. Now you can leave it like this, negative 90 plus theta, but I prefer to write it as theta minus 90. I prefer to have my positive first. It's just a personal preference. You can also write it as minus 90 plus theta. It's up to you. So I'm going to write my second reduction formula for quadrant 4 as theta minus 90. Now, let's move on to the next part. So when we were dealing with our positive angles, we started with quadrant 1 and moved into quadrant 2. So our next point is going to be to take the angles, or rather the reduction formula from quadrant 2 and multiply it by a negative in order for us to get our second point on our negative angles. Now, if you look at our negative angles, we're starting with quadrant 4. Our next point is going to be quadrant 3. Of course, like I mentioned earlier, we're moving in this direction. Okay, so let us write down our reduction angles from our positive cost diagram. So within quadrant 2 in our positive cost diagram, we had 180 minus theta, and we had 90 plus theta. So let us multiply this by a negative. So if we were to multiply 180 minus theta, we are then going to end up with theta minus 180. Keep in mind, I prefer to put the positive first. So you're just saying 180 times negative, you get negative 180. Negative theta times negative theta times. Now let us look at the 90 plus theta. So if we multiply this by a negative sign, we are then going to end up with negative theta minus 90. So in this case, both are negative, and I've been putting theta first, so I'm just going to have negative theta minus 90. Now, let us identify what is going to be positive and what is going to be negative within our third quadrant. So if we look at our third quadrant, we have T, which represents tan. So we know that only tan of theta or tan of our angle is going to be positive, whereas sine theta and cos theta will be negative. So far we've done quadrant 4 and we've done quadrant 3. Let us move on to, which is our third point started. Now, if we look at our third point after starting, when we're dealing with our positive angles, quadrant 1 is our first point of starting. Quadrant 2 is our second point of starting. Quadrant 3 is our third point after we've started. So we are now going to take the reduction formula of quadrant 3 and turn it into a negative. So it's going to be 180 plus theta. So if we have 180 degrees plus theta, and if we multiply that by a negative, we will end up with negative 180 minus theta. And I've been putting theta first the whole time. It's just a personal preference. You can put the number first. It doesn't really matter. So that is then going to be negative theta minus 180 if I swap them around. So my reduction formula within my quadrant 2 of my negative angles is going to be minus theta minus 180. Now, the reason that we do these negative angles is just to make it easier for ourselves when we have a negative reduction formula and we're supposed to reduce or simplify that. So we've identified the reduction formula within quadrant 2. Let us now ask ourselves what is going to be positive and what is going to be negative within quadrant 2. Now we can see an S within quadrant 2. So we automatically know that sine is going to be positive, which means everything else is going to be negative. Our cos of theta is going to be negative, and our tan of theta is also going to be negative. So that is quadrant 4, quadrant 3, and quadrant 2 completed. Let us look at our ending point, which is quadrant 1. So where did we end in our positive cos diagram? We ended in quadrant 4. So we are going to take the reduction formula from quadrant 4 and apply it to our new ending point within our negative cos diagram. So 360 minus theta. So 360 minus theta, like we've been doing the whole time, all we do is we multiply this by a negative, so it is then going to become negative 360 plus theta. And if we rearrange this to have the positive term first, it's going to be theta minus 360. So my reduction formula in my negative angles cos diagram within quadrant 1 is going to be theta minus 360. Now, let us discuss what is going to be positive and what is going to be negative within quadrant 1. So because we have A within quadrant 1, that means everything or all is going to be positive, which means sine theta is going to be positive, cos theta is going to be positive, and tan theta is also going to be positive. Now that is our negative angles and our positive angles cast diagram. All you need to do is remember the positive angles. That will help you get your negative angles. Now, let's move on to co-ratios or co-functions, followed by identities and formulas. Thereafter, we will move on to some past paper questions for us to see how are we going to apply our theory to actual questions. Now, something important to take note of whenever you're dealing with co-functions or co-ratios, whichever you want to call it, indication of 90. In order for you to identify 90, that is important. So we have a right angle triangle on the right. Let's make this angle theta, which would then make this angle 90 minus theta. Let's label these A, B, C. Let's identify or try and see how do we get this angle of 90 minus theta. For students that don't see that it is 90 minus theta. So if we were to add up all three angles of our triangle, A plus B plus C, what would that be equal to? We know that all three interior angles of a triangle are equal to 180 degrees. A is unknown, B is 90, and C is unknown. So A, actually C is theta, it's not unknown. So B is 90 degrees and C is theta, and that is equal to 180 degrees. Now if we move 90 plus theta to the other side, A is therefore going to be 180 minus 90 minus theta, which will therefore give us a value of A as 90 minus theta. So students that don't understand how we arrived at 90 minus theta, that is basically what you do. A student that has your mic unmuted, please can you mute yourself if you're not asking a question. So we have our angle theta, we have our angle 90 minus theta. Now let's assign our sides values. So let's have this as y, let's make this x, and let's make this r. So let's try and find what is sine of theta going to be equal to. So we know that sine theta is going to be equal to our opposite side. Keep in mind our reference point is this. So think of it as though you were standing at that point theta. That angle theta is you. Now when you're standing at the angle theta, what is opposite you? It's y. So y is our opposite over our hypotenuse, which is our side opposite 90 degrees. This is our 90 degrees. What side is opposite that? It's r. So sine theta is therefore equal to y over r. Now, if we look at cos theta represents our adjacent. We know that our adjacent is what is under theta, the side under theta. So if theta is here, what is under theta? The side here, which is x. So in this case, x is going to represent our adjacent side, and we already identified the hypotenuse as r. So cos theta will therefore be x over r. Now, let us use a different reference point. Let us stand at this point A. So if we are standing at A, our opposite and our adjacent are now going to change. So let us identify what is sine of 90 minus theta. Standing at that new point, which is 90 minus theta or A. What is opposite 90 minus theta? it's now x. So this is going to be x over the hypotenuse, which remains the same, r. If we were to look at cos of 90 minus theta, what is cos of 90 minus theta going to be equal to? We know that cos deals with your adjacent side. And our adjacent side is the side under the angle. So if you look at 90 minus theta, this is the side under the angle, this y. So our adjacent is going to be y over our hypotenuse, which is r. So if you notice, sine theta is equal to y over r. But cos of 90 minus theta is also equal to y over r. And cos of theta is equal to x over r. If you notice, sine of 90 minus theta is also equal to x over r. So that is how we can build the relationships between sine of theta, cos of theta, sine of 90 minus theta, and cos of 90 minus theta. It's because sine theta is equal to cos of 90 minus theta, and cos theta is equal to sine of 90 minus theta. Now, this is important because you do get questions regarding co-ratios and co-functions within your exam papers, and you are meant to reduce or to simplify those terms. So hopefully this should help you understanding when you are dealing with co-functions or co-ratios. Now, let's move on to our last part before we okay, someone is asking, wait, for sine, it's positive in 180 minus theta. Okay, so we won't, it's negative b1, negative 180 plus theta. Fahima, are you referring to, okay, I think you're referring to the negative cos diagram, but are you referring to quadrant 1, 2, 3, or 4? Please advise in the chats quadrant 2. Okay, so quadrant 2 is when sine is positive. That's fine. Your question is 180 minus theta. Okay, so keep in mind that we're not moving in the same direction. When we were dealing with our positive cos diagram, we went from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. Now, when we are dealing with our negative cos diagram, we are now going to go from quadrant 4 to quadrant 3 to quadrant 2 to quadrant 1. Essentially, we are moving in reverse, right? So if we were to write this, let's just write it down here. So when we were dealing with positives, right, it was quadrant 1, which was theta. I'm not going to use the co-ratios for now. So we went quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. Okay, now when we're dealing with negatives, what we are now going to do is we're going to go backwards. So we're going to go from quadrant 4, but our quadrant 4 is going to get the same reduction formula as quadrant 1. Reason being is our starting points are different. So this multiplied by a negative and then write it down. It's going to give you negative theta. Then quadrant 3. Multiply this by negative and then write your answer. Negative theta times negative gives you positive. 180 times negative gives you minus 180. Then we move on to the next one, quadrant 2. So multiply the reduction formula from this quadrant 3 by a negative, you're going to get negative theta, negative 180. Then move on to your next one, quadrant 1, because that's our ending point now. So take your reduction formula from your previous ending point, multiply it by a negative, and you're going to end up with theta minus 360. If the starting points, ending points, and the directions were confusing you, what I would do is I would recommend learning this. So write out, when you're dealing with positives, you start at 1, 2, 3, 4. When you're dealing with negatives, you start at 4, 3, 2, 1. You're working backwards. So just take it in line. The first one multiplied by negative, plug it into the bottom position. The second one multiplied by negative, plug it into the bottom position. The third one multiplied by negative, plug it into the bottom position. The fourth one multiplied by negative, plug it into the bottom position. So FIMA, hopefully that should be able to assist you. You can do the same thing with the co-ratios and co-functions within quadrant 1 and 2. I just left it out for this. Then we had another question. Can you repeat how we get 90 minus theta? So how we get 90 minus theta is just by adding up all three interior angles of our triangle. So if we were to add up A plus B plus C equals 180, that is all three interior angles of our triangle. Now we know that B has a value of 90, C has a value of theta. Now, if we were to solve for A, we would then need to take this to the other side and it would become negative. So we would then have angle A equals 180 minus 90 minus theta. Therefore, angle A is then going to give us 90 minus theta, because 180 minus 90 gives us 90. So hopefully you should be okay with that now. Let's see. May I ask, why is sine in 90 plus theta and 90 minus theta written as x over r and not y over r? Okay, so sine theta is opposite over hypotenuse, whereas cos of 90 minus theta is adjacent over hypotenuse. In this case, the opposite and the adjacent becomes the same value because you're looking at it from a different reference point. Sandra, say for example that you are at this point C, right? This is you're standing here. Now, where would your opposite be in terms of AB or BC? Your opposite would be Y. That is why we have Y over our hypotenuse. But let's say, for example, you are now standing at point A, so you've moved positions. Instead of being at C, you now moved positions to point A. So where would your new opposite be? Your new opposite would be X instead of Y. Y would now be considered an adjacent side. So it's because of your positions. If your position changes, the opposite and adjacent also change. Your sides are dependent on your position. It's in reference to something. For example, if you are standing next to your friend could be on your left side. But from the position of your friend, her friend could be on the right side. So if this is let's call this person A, let's call this person B. So if both of these students were asked, is your friend to the left or right of you? Both would have opposite answers because their reference point is different. Friend A would be to the left of friend B, whereas friend B would be to the, whereas friend A would be to the friend B would be to the right of friend A, whereas friend A would be to the left of friend B. Sorry about that. So depending on your reference point, your positions, the positions of your opposites and your adjacents would be different. So that's the whole point of this. Okay, so there doesn't seem to be any more questions. So let us proceed. So identities. What identities should you know within grade 12 in order for you to successfully answer most of your trigonometry questions? So at this point, you should know the identity of tan theta equals sine theta over cos theta. Now, it doesn't always have to be theta. You could use alpha, you could use beta, a, c, x, y, z. It doesn't really matter. That theta just represents any angle. So tan of any angle would be sine theta over cos theta. Now, please don't get confused. There's something that I've seen that sometimes students get confused with. If you have sine A over cos B, this is not tan AB. It's not tan A and it's not tan B. This does not give you tan. It has to be sine of the same angle over cos of the same angle. If the angles are different, it's not tan. Okay, so let's move on to the next thing. Tan squared of theta is equal to, same thing, only difference is you're using squared. And the same rule applies, it has to be the same angles. Something else that you should know is sine squared theta plus cos squared theta equals 1. Now, just as before with the tan, you have to have the same angle. It has to be sine squared of the same angle plus plus cos squared of the same angle. If you have sine squared A plus cos squared B, it's not going to give you 1 unless A and B are the same angle. Now, this can also be turned into 1 minus cos squared theta, which will give you sine squared theta. So if you have sine squared theta within one of your expressions that you're trying to simplify, you're trying to expand or change, you can turn sine squared theta into 1 minus cos squared theta. And if you have 1 minus cos squared theta, you can change that into sine squared theta. Another identity that is produced from this is 1 minus sine squared theta. That then becomes cos squared theta. So I'm not recreating new identities with 1 minus cos squared theta and 1 minus sine squared theta. All I'm doing is moving either sine or cos squared to the other side. So if I want to solve for sine squared theta, I'll move cos squared theta to the right. It's going to become negative cos squared theta. That's how I ended up with 1 minus cos squared theta equals sine squared theta. I'm just simplifying, or I'm solving for either sine or cos using the same identity. I'm not using new identities. Something else that you should know is your double angle formulas. Now, sine of 2 theta, which is a double angle formula, gives you 2 sine theta cos theta. If it's written as 4 sine theta cos theta, you can simplify, or you can break up 4 into 2 times 2. That'll give you 2 sine 2 theta. So it's important to be able to play around with your identities or your formulas. Now, when we're dealing with cos 2 theta, now this is special because it's equal to 3 different identities. You can use whichever you want. It's completely up to you. I would suggest trying to identify which is the best identity for the current situation that you were dealing with. I would recommend practice to identify that. So one of the identities is cos squared of theta minus sine squared of theta. Now, please don't get confused with sine squared theta plus cos squared theta and sine squared theta minus, cos squared theta minus sine squared theta. They're not the same thing. One has a plus, one has a minus. Or another way of thinking about it is sine squared theta is positive in the first one, but negative in the second one. And cos squared theta is still positive, but because that sine squared theta is negative, it doesn't make it the same identity. This can also be broken up into your difference of two squares. So cos theta minus sine theta and cos theta plus sine theta. So the reason I bring this up is because in a lot of prove the left-hand side equals the right-hand side or simplifying trigonometric expressions, we use this property, or we use the fact that cos squared theta minus sine squared theta is a difference of two squares. So it is used a lot. So I would go back to your algebra notes and try and train yourself to identify difference of two squares. So next we have 1 minus 2 sine squared theta and 2 cos squared theta minus 1. So all three are double angle formulas for cos 2 theta. Now, lastly, let us do our compound angle formulas, then we can move on into some questions. So our compound angle formulas are cos of A plus B, cos of A minus B, sine of A plus B, and sine of A minus B. So cos of A plus B, because you're dealing with cos, because you have cos in the formula, you'll have negative. Think of cos as opposite. So cos A, cos B minus sine A, sine B. And our second formula would be cos A, cos B plus sine A, sine B. Now sine formula stays the same. If it's a plus, you'll put a plus. If it's a minus, you'll put a minus. So this will be sine A cos B plus cos A sine B. This will be sine A cos B minus cos A sine B. I would recommend that you learn to identify both the left and the right hand side of your compound angle formulas because they are used frequently in grade 12. So make sure that you are able to identify both sides. Now, we have a question. Double angles. May you please repeat the part you mentioned, sine 4 something after talking about, oh, okay. So what I mentioned regarding your double angle formula for sine 2 theta, it can be, okay, so let's say you have 4 sine theta cos theta, for example. Now you know that the double angle formula is 2 sine theta cos theta, not 4 sine theta cos theta, right? So what do? Do you get stuck and give up because the 4 is not a 2? Do you skip it and leave the question and lose all of those marks? We just break up 4 into 2 and 2, right? Why must we lose marks when we can so easily gain them? So 4 can be broken up into 2 times 2 sine theta cos theta. Now from here we can see our double angle formula 2 sine theta cos theta. So we bring down this 2 because we're not dealing with it, but this entire part here becomes our sine double angle formula, which is sine 2 theta. So that's basically what I mentioned. You can get questions like this. I have seen a few. Some other popular questions relating to your double angle formula that I've seen is if you have sine theta cos theta. And okay, so like I was saying, we have sine theta cos theta. Now, how do we get the sine theta cos theta to become sine 2 theta? Because for whatever question we're dealing with, we now somehow need to get the sine theta cos theta to be 2 sine theta cos theta. So we can't now just go and put a 2 and proceed like nothing happened, right? It doesn't work like that. So how do we turn 1 sine theta cos theta into 2 sine theta cos theta? The reason I said 1 is because we know that this is a variable, right? If you want to think about it like that. Let's say, for example, this whole thing represented x, if you want to think about it like that. If there's no number in front of x, does that not mean that we are dealing with an invisible 1? Because most of the time, when you don't have a number in front of your variable, it means that there's a 1 in front of that variable, right? So essentially, what we have here is 1 sine theta cos theta. So we need to ask ourselves, how do we turn 1 into a 2? Now, we know that when we're dealing with expressions, we can't just multiply. It doesn't work like that. We have to factorize. So if we take out something, we need to be left with 2. So what are we going to take out to be left with 2? If you don't automatically see the answer, I would recommend creating an equation, right? So you used to do this if you used to do bonds, I'm sure most of you had bonds books in primary school, right? So the question would always be something plus 1 gives us 2. Then we'd ask ourselves, okay, if I have 1 sweet, what do I do to get 2 sweets? You just add 1 sweet, right? So we're all familiar with that concept. But now we are trying to take out a common factor. And we know that whenever we take out a common factor, it's the same thing as dividing. So we have 1 and we're taking out a common factor that we do not know. But at the end, we must have a 2. So create an equation. 1 divided by our common factor, let's call this common factor CF. Okay, so 1 divided by our common factor must give us a 2. So we know that 1 over CF equals 2 is the same as saying CF equals 1 over 2. So our common factor is a half. So if we were to take out a half from this expression, we'd be left with 2 at the end. So let's do that. So if we factor out a half, we'd be left with 2 sine theta cos theta. And to check if you're right, multiply that half back into the expression or back into the brackets. A half times 2 is going to give you 1, so you'll go back to the original. So based on this, we can see that within our brackets, we have our sine 2 theta, right? So that's going to give us a half sine 2 theta. So what we need to do is basically play around with the principles or the properties of numbers that we already know, because we all know how to factorize or how to take out a common factor, right? So essentially, trig is just basically playing with algebra rules that you already know. They just added in some identities. That's it. Yeah. So hopefully that does answer the question that was asked. The student that has your mic unmuted, do you have a question? Okay, guys, if you're going to unmute yourself and have a conversation with other people, please, can you exit the session? It's kind of disturbing and rude. Okay, so that's basically everything you should know. Okay. We've done our positive angle cost diagram. We've done our negative angle cost diagram. We've done co-ratios or co-functions, whichever one you want to call it. And we've done what identities you should know. So before we proceed to some questions with the remainder of the time that we have left, does anyone have any questions or anything they'd like to ask? Let's see. Okay, someone has a question. If we had another number besides 1, which would we divide with, or how would we get to sine 2 theta? Okay, if you had another number, it's the exact same process. Remember, the process stays the same, right? You don't ever change the process. So it's the same process. If we had another number, let's use an odd number. Let's use 3, for example. So if we had the number 3 sine theta cos theta. So if we had this number 3 sine theta cos theta, how do we turn this into a double angle sine formula? We repeat the exact same process. Ask ourselves, we have 3 this time. So 3 divided by our common factor. Right. We have 3 sine theta cos theta, right? Now we need to somehow turn this into sine 2 theta, or double angle sine formula. So it's the exact same process. We ask ourselves, what do we need to factor out from our coefficient in order for that coefficient to become a 2, right? So our coefficient is 3. We need to divide it by some common factor, because that's what taking out a common factor is. It's dividing, right? So we need to divide it by that common factor, and that should give us 2. So essentially your formula is just the coefficient divided by your common factor, and that should give you 2. So we know that our common factor will then be equal to 1 over 3. Sorry, 2 over 3. No, wait, sorry. If that's at the bottom, swap places, it's going to be 3 over 2, not, sorry about that. It's going to become 3 over 2. So if we take out a common factor of 3 over 2, from here, we would be left with 2 sine theta cos theta. And that, if you want to double check your answer, multiply 3 over 2 times 2. You'll end up with your 3 again. So whatever you do, just double check always. Just multiply the 2. If you end up with your original answer, that means you're on the right track. So we know whatever's in the bracket, there's 2 sine theta cos theta. That is our sine 2 theta, our double angle formula. So we would then end up with 3 over 2 sine 2 theta. Excuse me. So we would end up with 3 over 2 sine 2 theta. The person that asked that question, hopefully you should be okay now.